Imagine the lights suddenly cutting out in a massive data center. We're talking servers crashing, vital data getting corrupted, and literally millions of dollars evaporating in mere seconds. Pretty catastrophic, right? Well, that is exactly why our modern digital infrastructure relies so heavily on uninterruptible power supply, or UPS, systems. Welcome to today's Explainer. We're going to unpack the heavy-duty engineering that prevents these total blackouts, UPS redundancy design. And specifically, we'll be breaking down the 2 out of 3 versus the 3 out of 4 architectures.
Now, you've probably heard infrastructure engineers throwing around terms like 2 out of 3 or 3 out of 4 and thought, okay, what exactly is the difference? Honestly, it can sound like impenetrable engineering jargon when you're trying to plan critical facilities, but I promise you the underlying logic is fascinating and it's surprisingly straightforward. At the end of the day, it's all about ensuring the power never, ever stops.
All right, let's dive into this. Here is our roadmap for today. First, we'll tackle the core question of uninterruptible systems. Next, what is N+1 redundancy? Then we'll examine the 2 out of 3 architecture, followed closely by the 3 out of 4 architecture. And finally, we'll wrap up with the core differences at a glance.
Section 1. The core question of uninterruptible systems. It's all about finding that absolute perfect balance between capacity and backup.
You see, the core concept of redundancy really always asks the exact same vital question. How many total UPS units are strictly needed to handle your facility's massive power load, and exactly how many units are you keeping ready as backups? Think of it like a team carrying a heavy sofa up a flight of stairs. You need to know exactly how many people are required just to lift the weight, and how many are standing by on the sidelines ready to jump in just in case someone slips.
Moving to Section 2, what is N+1 redundancy? This is basically the golden rule of survivability.
First up, we have the letter N. This stands for your required quantity. It's the absolute minimum number of UPS units you need for the entire facility to operate normally under a full load. So the crucial point here is that N represents the non-negotiable baseline of power. If your capacity ever drops below N, well, your servers are going dark.
Next, you tack on that +1, which represents the backup quantity. This is the extra unit kept completely in reserve. And why do we need it? Because it is inevitable that an active unit will suddenly fail, or you'll have to shut one down for routine maintenance. That +1 is your ultimate safety net. It guarantees that a single point of failure doesn't result in a totally catastrophic system blackout. Which brings us to Section 3, the 2 out of 3 architecture, the perfect harmony of simplicity and stability.
So the phrase 2 out of 3 is actually wonderfully literal. You have 3 total units installed in the facility. A minimum of 2 of those must operate to handle the total load, while that remaining 1 acts as your dedicated backup. Let's use a practical math example from our source material here. If your facility has a total required power load of 2,000 kilowatts, you would install a total of 3 1,000 kilowatt UPS units.
To put that into perspective, each of those 3 units represents a potential 50% of the total required capacity. So any 2 of these units combining forces will easily hit that 100% mark needed for your load. That 3rd unit, that's your invisible shield, fully capable of stepping in instantly if one of the others goes down.
But wait, what happens on a normal Tuesday when everything is working perfectly? Under normal daily operation, the system doesn't just leave one machine sitting there totally idle gathering dust. Instead, all 3 units share the work evenly. Because there are 3 units handling what is technically a 2-unit load, each individual UPS operates at about 66.6% of its maximum capacity. That leaves roughly 33.4% totally unused and ready to go.
So what's the ultimate takeaway for this setup? Well, the major advantage is incredibly high survivability. Even if 1 unit completely gives out, the remaining 2 instantly cover 100% of the load without even breaking a sweat. The flip side, though, is that the baseline stress on the machines is a little bit higher during normal operations, since they're constantly running at that 66.6% capacity mark.
All right, Section 4, the 3 out of 4 architecture. This is all about scale and economic expansion.
Now in a 3 out of 4 setup, you install 4 total units. A minimum of 3 must operate to handle the total load, and 1 acts as your backup. For example, if your facility has a massive load of 3,000 kilowatts, you don't go out and buy 3 gigantic 1,500 kilowatt machines. Instead, you install 4 1,000 kilowatt units. You still have that vital +1 safety net, but you've essentially sliced the pie into more pieces.
What's really fascinating here is how the individual unit requirements shrink way down. Because 3 units are required to hit 100% capacity, each individual unit only needs to be sized to handle 33.3% of the total load.
And guys, this is a massive deal for gigantic facilities. Why? Because it saves incredible amounts of initial investment on giant, oversized equipment. Smaller individual units are just way cheaper and much easier to source.
However, there is a catch when it comes to daily operations for this specific setup. Because the individual units are smaller relative to the total enormous load, they actually have to work a little bit harder during normal incident-free operation. When all 4 units are sharing the work evenly, each one is hitting a 75% load share, leaving only 25% unused capacity per unit.
The advantages of the 3 out of 4 system are absolutely compelling. It is highly economical, highly scalable, and uses smaller individual equipment. It's a total financial win for massive power demands. But the disadvantages? You now have 4 complex machines to physically synchronize instead of 3, which means a much more complex control circuit. Plus, as we just mentioned, there's that slightly higher normal load rate of 75%.
Which brings us to Section 5, Core Differences at a Glance. How do you know which design is right for you?
Let's put them head to head and look at the numbers. The 2 out of 3 uses 3 total units, sharing a 66.6% normal load, and requires each unit to cover 50% of the total capacity. It's beautifully simple and highly stable. On the flip side, the 3 out of 4 uses 4 total units, runs at a higher 75% normal load, but only requires each unit to cover 33.3% of the total capacity. So the strict trade-off for that economical sizing is a noticeably more complex control system.
Now, how does this actually play out in the real world? Because that's the most important part. This isn't about one design being inherently right or wrong. It's about strategically choosing simplicity over scalability depending on the sheer size of the facility. The 2 out of 3 architecture is perfectly ideal for small to medium data centers, hospitals, and standard factories where simplicity and maximum stability are absolutely paramount. Meanwhile, the 3 out of 4 architecture is the absolute go-to for massive internet data centers and huge industrial plants where scalability and equipment economics have to take top priority.
So, we've totally mastered the fundamentals of the N+1 structure today and exactly how facilities flawlessly balance capacity with backup. But, the world of power redundancy goes even deeper. Think about this. What happens when the stakes are so unimaginably high that you need an N+2 structure just to survive double simultaneous failures? How do these units actually parallel their control systems safely, and what crucial role does a static transfer switch play in keeping those servers humming? Keep those incredible challenges in mind as you consider the hidden engineering that literally powers our entire digital world. Thanks so much for joining me on this explainer, and keep questioning how the systems around you really work.